Number 1, a store receives 2,000 decks of popular trading cards. The number of decks in a function we're going to call D, and that's going to be the number of days T since the shipment arrived. So we've got our variables here. D is our number of decks, and T is our number of days. Calculate the average rate of change for the following intervals. So average rate of change is where you take the difference, which means subtract. So the difference divided by really like the interval, if you want to think about it like that. But the difference in the function divided by the interval. So we want to go days 0 to 5. So you're going to do this way. So you're going to subtract these. You're going to do 1,283, always doing the new measurement first. Okay, and then minus the first measurement. And then divided by that interval, which is really just the difference in the time value too. So you could think of it as doing 5 minus 0 down here too, or just divided by 5 days because that's how long that took. So this is negative 717 divided by 5. So the average rate of change from day 0 to day 5 was negative 143.4. So then from day 15 to 20, so now we're looking here. So here's our interval, and we're going to subtract these. So we're going to do 338 minus 528, and then we're going to divide it by that interval again. You can think of it as subtracting this to figure out the interval, or you might just know that that was 5 years. So then this is negative 190 divided by 5. So the average rate of change from day 15 to day 20 was negative 38. So meaning, on average in this first one, they sold 143 decks each day. And on average from day 15 to day 20, they sold 38 decks a day. Number 2, a study was conducted to analyze the effects on deer population in a particular area. Let F be an exponential function that gives the population of deer T years after the study began. If F of T equals A times B to the T, and the population is increasing, select all statements that must be true. So let me just quick sketch. So it's exponential. So remember that exponential functions are going to look something like this if they're exponential and they're growing, right? So this says increasing and it's exponential. So select all statements that are true. Remember that B right here, this is your growth factor. So in order for your population to be increasing like it is here, that would mean that B needs to be greater than 1 so that you're getting back more than you started with, versus if it's less than 1, then you're getting back less than you started with. For C, it says the average rate of change from 0 to 5. So let's just pretend that that's here. Is less than the average rate of change from year 5 to year 15. So let's say that's this. So I'm just drawing in kind of the slope because average rate of change is the slope. So the line connecting those 2 points at 0 years and 5 years versus 10 years and 15. And so if you have exponential growth, then the average rate of change is true, that it's less on these lower numbers, right? 0 to 5 versus to the left, it's lower than it is to the right because it's increasing. So that slope is getting steeper as the numbers get bigger. So C would be good, D would be bad. And then it says that A needs to be greater than 0, and A is that initial population, and that is also true. If E was less than 0, then you'd have something like this. And then it's, all the numbers are negative. And so then the population, first of all, the population can't be negative. Second of all, if it was, then all of the numbers would be negative, so they wouldn't be increasing. Number 3, function f models the population in thousands of a city T years after 1930. The average rate of change from T equals 0 to T equals 70 is approximately 14,000. Is this value a good way to describe the population change of the city over that time period? Explain or show your reasoning. So when you, again, do average rate of change, so here's T equals 0, and here's T equals 70. Average rate of change means if that population just, or whatever the data is, changed consistently over that time period, meaning the slope of a linear line connecting those 2 points. So this right here represents the average rate of change. Now, is that a good indicator of all of this data? And I would argue no, because it's not touching any of the data, right? So in the beginning, the population isn't changing very much, right? Like it's just growing by a little bit. So in the beginning, the population growth isn't very fast. Versus at the end here, this is growing significantly once you start getting out to years like 50 to 60, right? Then that growth is getting, I mean, and then here, like then the growth is much more rapid. So it's not, the average rate really doesn't do it much justice here. So no, in the beginning, the population growth isn't very fast. Then as the time goes on, the population grows at a much faster rate. So again, those are my words. You can say it in your own words and change that a little bit. But the idea here is that the average rate of change, doesn't hit much of these data points, and the population isn't changing consistently. So it's not constantly going up by 200 people a year. It gets more and more as the years go on. Number 4, the function f gives the number of copies a book has sold W weeks after it was published. This equation defines the function. Select all domains for which the average rate of change could be a good measure. So let's just think about what this function looks like. So it's going to be exponential, and it's going to be exponential growth, right? It's growing by a factor of 2, starting at 500. So it's going to look something like this. So average, and really probably steeper than this. So let's think about it. So at 500, then the next one, at 1 week, it's going to be at 1,000. At 2 weeks, it's going to be at 2,000, right? And so you could, draw yourself a more accurate sketch. I'm going to actually get rid of the axes here, and I'm just going to draw an exponential growth equation like this. So we know it's going to be something like that. So select all domains for which the average rate of change could be a good measure for the number of books sold. So when we're looking at this, remember, average rate of change is the straight line that connects the values at 0 and at 2. So if we're sitting here at 0 and at 2, your line is maybe like this. So that's a decent measure. Like, that's not bad for this one. So I would say that one would be fine from 0 to 2. If we're looking at from 0 to 7, so if we're looking 0 to 7, let's say 7's about here, that's not as good, right? It skips a bunch of this data down here. And so I would argue that that's not a very good domain for that. If we did 5 to 7, so then 5's probably here to 7, now pretty good. So C would be, So C would be pretty good because that slope between kind of those 2 points is pretty close to what the exponential function would be doing at that time. 5 to 10. So 5 to 10, again, and 10 is probably like way up here somewhere. Okay. Again, not very good. Those are too far apart. So the data is changing too drastically and too differently. Then the last one, 0 to 10, surely not, right? Like that one's for sure not going to be here up to there. No, it's going to miss a ton of this data. So that one is not going to be good either. So the average rate of change is pretty good on exponential functions when your data is close together, right? When you're looking at, these are only 2 apart. These are 7 apart. These are 2 apart. 5, 10. So the closer they are, the better the average rate of change will model it. Number 5, the graph shows a bacteria population decreasing exponentially over time. This equation gives the size of the second population. So this one's the first population. And then this equation gives a second population where H is the number of hours since it was measured at 1 million. Which bacterial population decays more quickly? So let me change this color here. So this one, here's the decay factor, right? So this one, and this is population 2, right? So the second population, the growth factor, the B value equals 2/3. Okay, so we know that that's decreasing, or the growth factor is 2/3. So that's keeping about 66, right, percent or 67%. So if we did 2 divided by 3, let me just do it as a decimal for you first. So 2 divided by 3 is 0.6 repeating. So then it's keeping about 67% of its population each year, or hour, I guess, in this case. So then the first population, we need to figure out what its growth factor is. So let's take a look at 2 of these values. And remember that factor means we're going to be dividing. So this one's at 250 here and at 150 here. Okay, so if we do 150 divided by 250, so the new measurement divided by the original measurement. And if you simplify this fraction, we can divide by 10. We can divide both of these by 5, and we get 3/5 for the B value here, which means that this one is 0.6 or 60% each hour. And this is this is how much is left, right? So in this case, which one is decaying more quickly would be this one, because it's losing 40% each hour, where this one is losing 33% each hour if you take 100 minus 67 or 100 minus 40. So this one is decreasing at a faster rate. Number 6, a moth population P is modeled by this equation, where W is the number of weeks since the population was first measured. What was the moth population when it was first measured? So first measured is your initial population. So right there at 500,000, you can just steal it from the equation. You also, if you forget that, you can plug in W equals 0 and use your calculator, and it'll give you back 500,000 as well. What was the moth population after 1 week? Well, this is decreasing by a half, right? So the growth factor is half as much each time. So after 1 week, half of 500,000 is 250,000. So you maybe can do that without your calculator. Otherwise, if not, then you're typing in this into your calculator, 500,000 times 1/2 to the 1, and that's going to give you 250,000. So then after a week and a half, so this one you'll likely need your calculator for, type in 500,000 times 1/2 to the 1.5. So put that in as an exponent there, and then have your calculator calculate it for you. And it's like 176,776 point something. So around 176,777, or maybe you even want to round it to just say 177,000. Then it says use technology to graph the population and figure out when it falls below 10,000. So I went to Desmos and graphed this. Okay, I made sure to change my window so that I could see what was going on. So notice for my x's, you know, my minimum x is about -1, and then my maximum x is about 8. And then for y's, I put in like -10,000. And then my top value is 500,000. Well, really 550. Just so that you can see what's going on. So 550,000. So you can see what's happening. Then what I did is you can see that we want to figure out when this falls below 10,000. So what I did was graphed the line y equals 10,000. So that line is y equals 10,000. So you can graph both of them on the same grid. And then you can click on it and you can click to see where they intersect. So where does this exponential graph hit 10,000? And that's at 5.644. And what was this? Weeks. So after, you know, sometime after 5.6 weeks, right? Is when that would happen. So after 5.644 weeks, then the population would dip below 10,000. Number 7, given R value that would indicate a line of best fit has a positive slope and models the data well. So remember, R values can be anywhere from -1 up to 1. And the closer they are to -1 or 1 is the better that they model the data. If they're closer to +1, then it's a positive slope. -1, then it's a negative slope. So we want this to be positive and model the data well. So something like an R value of positive 0.95 or 0.96, 0.97, 0.99, anything. I would argue anything probably like 0.9 and higher, or 0.85 and higher would model the data well. Number 8, the size of a district and the number of parks in it have a weak positive relationship. Explain what it means to have a weak positive relationship. So having a weak relationship means that this is not going to model the data well. Okay, so if you have your line of best fit, when you create it using this data, the line of best fit will not model the data very well. Meaning it doesn't predict it well. So predictions won't be accurate, won't be very accurate. Right? That line of best fit is not going to hit the data points. Okay? It's not going to hit very many of them. And then positive means that there's, you know, some type of correlation, but not correlation, but the data points, like if you were to plot them, they seem to be going somewhat in an upward direction. So there's some indication that the more parks there are, the more bigger the district. The size of the district is bigger. But there's no strong correlation to that. But as as the parks increase, the size of the district seems to also be increasing. Okay, just not in a very correlated manner. Number 9, here's a graph of Hans' distance from home as he drives. Identify the intercepts of the graph and explain what they mean. So this first one here on our vertical intercept is 0, 10. And remember, this is time and this is distance. So at 0 minutes, when he starts traveling, he is 10 miles from home. Then the horizontal intercept here is 10, 0. So now, again, the first value is the time, the second value is the distance. So this is saying that in 10 minutes, he'll be at his house. So after 10 minutes, he is home, right? He's at his house. And you could say that in different ways too, right? Takes him 10 minutes to get home. So vertical intercept could be that's how far he is from his house. Horizontal is how long it took him to get home.